All right, all right. Good. I think we are good to go. We can start our class for this evening, even as I wait for a few of you more to join. Let me first check this audio. Okay. Right, I can see the connection. Okay, people are joining in. Okay, thank you. They will have a brief of a theory and some calculations. We want to do an example in concrete mix proportioning. So as usual, if you have any concern, you can raise it in the comment section. And as well as if you have any question, still is the same area to raise your comment or question. Also, don't forget to register your attendance by typing in your name and registration number. As a start, I always like to give a brief of what it is that we are doing here. So concrete mix design or proportioning. Sorry, excuse me. So concrete mix design or proportioning, all what we are doing is that we want to get the best ratio for our concrete mix in terms of the ingredients. We have been studying about the different ingredients for concrete. We have looked at three main when you are preparing the ordinary concrete. Then we talked of that our concrete will be made of the coarse aggregate. So of course we start with the coarse aggregate. We have the fine aggregate. We have the binder, which now in this case we are limiting ourselves to cement. And of course the water, which we said is expressed in terms of water to cement ratio. It's a ratio of the cement content. So why we do this proportioning? We want to get the appropriate proportions for either of these, because there is a certain strength that we want to achieve to assure the safety of our structure. Again, we do not want to use ratios which are uneconomical, okay? So you are trying, as an engineer, you are trying to balance between these two to produce a safe design. At the same time, you are looking at the client in terms of the economy. That's why, although, for example, we say there are nominal mixes, like, for example, class 20, we could say we just use 1:2:4, okay? Okay, 1:2:4, this is class 20. You could go with 1:2:4. But you may realize that you have got very good aggregates, okay, very strong aggregates, such that you don't need actually to use 4. Okay, you may use more of these to attain the strength. Maybe like something 1:2.5:5. So you are using less of cement and much of coarse aggregate, and still you are able to get a strength of 20 MPa. So you see, you have economized. Again, on the other side, you may realize that the aggregate you have from your side, they are not of that very good quality, right? Therefore, when you use this nominal mix ratio, you are targeting to get 20 MPa, you end up getting 15, okay? So you see, in terms of safety, you have not achieved that. So what do? You do the mix proportioning using now the properties of the aggregates that you determine, the one that you have. Therefore, you may realize that something to do with, let's say you need to use less of this, less of aggregate, more of cement. Maybe like 1:1, let's say 8 is to maybe 3.5 to attain a class of 20. So that's why don't always go for nominal. Okay, you may find like not many people do the mix designing because we say aggregate do not change as much. So if like working in a certain area, the aggregate may have relatively same proportion. But what if you're using new aggregates? What if your aggregates have got better properties? That's why we need to conduct a proper concrete mix proportioning. And there are many factors that you may need to consider. So the objective is to achieve the minimum strength as well as to make an economic concrete. So what the concept or the design philosophy of concrete mix, and in some books, you may realize that the word concrete mix design is referred to as concrete mix proportioning, because we are just looking at the optimal proportion or ratios. This is so that you don't confuse with concrete mix design or design of concrete structures, as you're going to see later on in your career. I think around 4th year or 5th year. Okay. So we assume, or the design philosophy is that the concrete strength is limited by the strength of cement, sand, and plus water. These are what you can say assumptions, or what we assume as we start. So issues of permeability and dry shrinkage. This is a durability aspect that is governed by the quality of the paste. The more denser, the more impermeable it is, the more durable your concrete. Of course, there are many factors that you may need to consider in designing a concrete. One is the grade. Which grade of concrete do you want to use? But I'm not interested in all that because you can go through them quickly. There are two methods that we approach for our case. Of course, there are other methods, but for us, we focus on two. One is the American Concrete Institute design method, while the other one, which I want us to focus on today, is a method by the British Mixed Design, British Research Establishment. So you might see the word BRE, and the department that produced this approach, or this design procedure, is called the Department of Environment. So you may see the method being referred to as DOA. Now, this method is very simple because the process of the design is divided into 5 stages. And in either of these stages, there is a certain aspect, whether it's a strength, whether it's water requirement, whether it's the aggregate, grading, the specific gravity, and so on and so forth. And that's why you realize, for us to design concrete, we need to understand the properties of our ingredient, the cement, the coarse aggregate, the fine aggregate, and water. Okay, so at this stage, as I raised earlier, you cannot proceed without having this manual. Of course, we are not going to look at everything in the manual, but everything is important. There are certain tables that we are going to refer to, but it's good for your future reference to have this manual, the one I send into your emails. So the 5 stages are here outlined, and we are going to follow them one by one so that we are able to know at each of the stage. Like stage 1, we need to select the target water cement ratio. What does this stage entails? What do we need to calculate? And there's some theory that we may need to refer to in the manual. Okay. So stage 1, because this is outright, and I hope that you have somewhere that you might be noting this. When you are designing your concrete, you need to know what is the target strength. What is the required characteristic strength at 28 days? And of course, I know at this stage you understand why we talk of 28 days. For example, do you want to have a strength of 20 MPa, 25, 30? Yeah, class 20, 25, 20, like that. Okay. Then, because of variability in concrete production, when you are producing your concrete, there will be variability. The amount of water may go slightly higher or lower. The aggregate may have varying, you measured a sample representative. Even though you did quartering, that was a representation. So whether you determine the density, the specific gravity of the aggregate to be like 2.5, you may realize that for the whole sample, the aggregate is varying. There are some which you have 2.55, 2.45, and so on and so forth. Because of that variability, if you just work with the characteristic strength, which is the strength that we need, you may miss. Therefore, we design for a higher strength. So what we call a target mean strength. We design for a higher strength by some margin. So this is the strength that we require. Let's say we are saying class 20, we add some margin. Let's say 5 or 10 or 8. We are going to see how you determine this margin so that you are targeting. It's like the way we say aim the sun, reach the moon. So you target maybe a strength of 25 MPa, you start getting issue to do with 23, 22, 21, and so on and so forth, which all falls under class 20. Okay, so you don't want to have a big margin because it will go to higher class, which you are not designing, and you do not want to have a very small margin, which you may be working on a very tight thread. As I said earlier, if you design your concrete, then you cast, after 28 days, you realize that the strength is below your target strength. You see, you have wasted the whole month. Okay, of course, at 7 days, we can approximate, we can extrapolate. Okay, so we design for a higher strength. Therefore, what we say is that we need a margin. We need to understand how do we determine this margin. Okay, And at this juncture, I want to refer to you to the manual that you have. A manual that you have, allow me to share it here. Okay. Okay. I hope it's clear on your side. I have shared the manual. This is on chapter 1, introduction. I have just mentioned about something that is appearing here. I wish it disappears. Okay. I wish it just disappears. It's covering the top page. Okay, it's moving. Okay. But it's not coming on your screen. I wonder what's happening. So in your manual, if you open, somebody who calling me. Somebody who is calling me slightly. Wacha nikupigie niko kwa meeting, eh? Sawa. Wacha nikupigie niko kwa meeting. Wacha nikupigie niko kwa meeting. Yeah, nitakupigia. Okay. Sorry for that interruption. This is what I wanted to share. Okay. I think when you are sharing because of I don't know whether it's internet or the settings, it's always slightly behind. Okay. So I do not expect you to start reading this, but I want you to open the manual. 1.1. This is what I started with by saying that mixed design is selecting the best proportion. And there are some properties that we are targeting. So you look at the text that I have highlighted, the first rectangle, that there are some properties that are specified. There are some workability that we need to achieve so that you can be able to work with our concrete. There is some strength that we are targeting, and there is an aspect of durability. We want to design a concrete of a certain durability. Now, what made me come here is the issue of strength margin. So you're saying that there will be variability in concrete strength. Therefore, we design our concrete to have a slightly higher mean strength than the target. Okay. And therefore, there is a certain margin that we need to input. Okay. Move with me to, I believe this should be chapter 2. Chapter 2. Chapter 2 on margin. Okay. If you come to chapter 2, yeah, we are here. Chapter 2, subsection 4.2, or part 2. We are saying, no, this is still part 1. Part 1, subsection 4. So this is 4.2. Just open your manual, page 4.2. It has been known that results are distributed, or results of concrete strength results are distributed, have got a normal distribution. I wanted to show you this figure. Okay. I wanted to show you this figure here. And as you can see, there is normal distribution. And as we are saying, my pen, I don't know, it's not writing here. I wish it could write. Maybe it's not supposed to write on a PDF. It should be. Okay. But don't worry. So we can use the pen. Tools, pen, or pencil tool. So what we are saying is that this is a normal distribution. Like if you have, let's say, cubes like samples for determining the strength of concrete, it's class 20. As we are going to see how to determine the compressive strength of concrete, in the lab, we make cubes. Yeah, we make cubes. So these cubes, of course, they have standard dimensions. Don't worry about that. We are going to reach there. So if you make like 100 or 1,000 or 20 or 10, you realize that although you casted your concrete using the same mix, but when you start testing the strength of these cubes, all of them will not have the exact value. They will not have like 20.0. Some will be 21, others 19, others 23, and so on and so forth. And the distribution, now if you plot that, if you plot, this is statistics now, if you plot the distribution of the results of the strength, the top being the mean, this is the mean value. Let's say maybe this is 20. So this is the mean value, 20. And the variation will be normal distribution. Usually normal distribution is like a bell. Okay. And if your specified characteristic strength, let's say, is 30, what we are saying is that we are assuming, okay, allow me just to use it in straight layman's language, because I know you guys, you are fresh from statistics class, okay? Or you are doing it either now or next semester. You realize that we talk of defective. There's some percentage defective that we do allow. That we are saying a certain value of all our sample, our specimen that we are testing, a certain percentage can be defective. For example, 5%, 10%, 2.5, 1, and so on and so forth. Now, why are we talking of the defective? We are trying to get the margin. The margin M, okay, sorry. The margin M is given by the value K times S, where K is dependent on the percentage defectives that we choose. Okay. Then S is the standard deviation. This S is the standard deviation. And this, from the manual, we are being given for a case whereby if we assume 5% defectives, that out of all our specimen, if there are 20 or 100, 5 of them we could assume that they are defective. Then the value of K is 1.64. Of course, these values have been obtained through a series of experiments, what we say numerical. These are empirical data. These are not from analytical. They are not derived from first principle. These are after test has been done. And as we are saying, and this is something that you'll have to embrace with time about our design, design manuals are developed after having combination of analytical as well as experimental work and field observations. Over time, a trade is observed, it's conducted in the lab, it's verified, it's confirmed to work to be true, then a standard design procedure is given. And now for this one, we are saying, the British Research Establishment, the Department of Environment in British, UK, after conducting tests with a variety of aggregates, they found this to be the distribution. It had been confirmed even locally. And therefore, for like 5% effective, they found K to be like that. So you can read more on this page to understand further, but I thought it's good to understand that. Also, if you do not want to calculate M, you can specify. You can say, I'm targeting class 20. So we say FC, specified characteristic strength, FC. FM, the target mean strength, is equals to FC plus the margin M. And this is the margin that we are calculating using this. K times standard deviation. Good. If you are to calculate it, use the formula M. If you are not to calculate it, you can say, I'm going to design for target strength, for a characteristic strength of 20, I'm going to have a margin of like 5 megapascals. So my target mean strength will be 25. So it all depends whether it will be given The margin is given. If it's not given, then you need to calculate, depending on the information that is there. But if you are the engineer, then you need to decide whether to calculate, whether to give a margin. Now, if you are to calculate, K, we have seen how we obtain it. How about a standard deviation? Now, again, from studies, so you see, even there's some calculation here. The beauty about this manual is that it have got worked examples. So a target mean strength. If you are targeting class 30, and you say the number of defective is 1.64, and S, the standard deviation, is given as 6.1, we are going to see whether you obtain 6.1. Then you can be able to say, if I'm designing for class 30, I will target class 40. So that if I miss class 40, the value I get will be above the value, strength of 30. Okay. Now, how do we get the standard deviation? The standard deviation, you can read that theory, but I want to show you the table where we do the standard deviation. And this is where now we come to mixed design proper. Part 1 is more of introduction and theory. Part 2 is the mixed design process. Part 3 of this manual is when now we have concrete, which is modified. So our focus for this class, because it's like an introduction, will be focusing on part 2. But you need part 1 to understand the theory. Now, the margin S is determined from table 2. Okay? The margin is determined from table 2. I'm just hoping that this is flowing even on your side. sorry, not table 2, figure 3. If you look at figure 3, if you look at this figure carefully, you're going to see that let me go back, I think, to let me go back to them. I was using a pen. So you see here, we are using figure 3 to get the standard deviation S, this value S. So that if you are to determine the target mean strength, which is equals to the characteristic strength, which is now the strength that we are designing for, plus the margin M, and the margin M is equals to K times S. And we have seen that K is determined from the percentage defective. Once you know what is a percentage defective, you can now go to the manual and see if it's 5, 10, 1, and so forth, what is K. S is obtained from this figure. And we are saying the vertical axis is the standard deviation. The horizontal axis is the characteristic strength. We have two curves, curve A and curve B. Curve A is when there are less than 20 results. Curve B is when the specimen that you are talking about are 20 or more. As I told you, the distribution curve is based on a number of tests of the same specimen. Like concrete class 20, you cast like 50 cubes. If your cubes are more than 20, then you read S from curve A, curve B. If they are less than 20, then you can read S from curve A. How do we read this? So what you do is, if your characteristic strength, the class strength of concrete that you are designing is, let's say, 20, you move up. Based on, if the values are based on more than 20 results, then you read across to get the value of S as 4. If, let's say, you are targeting, remember there is the target mean strength and the characteristic strength. The value here is characteristic, and characteristic represent the class of concrete that you are designing. The target is the value including the margin, the exaggerated value, let's say in quote. So if the characteristic strength, if you are designing class 30, you come to where that is, and if the results are less than 20, then you read the upper curve, curve A, then you go horizontally. Here you see the standard deviation is 8 newtons per millimeter squared. I'm just hoping that so far up to that point, we are together. Now I'm saying all this is done if M is not given. if the margin is not given. But if it's given, then you do not need to do all these calculations. Now, something that I need to mention at this stage is that there is page 11 of the manual, table 1. This is the standard form that we used to fill. So if the job title, like for your case here, is the assignment, okay, or group C assignment, group C1. If you are in the field, you could say, because you might be working for different clients, you could say this is Thika site, or is Nairobi Sifa Towers. This is just to refer. And this one, you are going to do it so much. Every time you have some specimen you get from the lab, from the field, you label it. The sheet that you are going to use to record your data, you also have to label accordingly, so that there will not be a mix-up. You can do wrong reporting. You do a proper test, but you report in the wrong, sheet. So that's why we label. So if you calculate now here, what you just need to do, characteristic strength, they specified at 28 days. If you say we are targeting class 20, you write 20 there. At how many days? 28 days. So the proportion defective, if you are told how many proportion defective, now where do you get the proportion defective? For if it's classwork, you'll be given, or you can be told to assume. But if you are in the field, you are the engineer, you decide, either through doing a number of tests, or through experience, okay? So if the percentage defective are 5, so what you realize is that in this form, there are some pages that we might not fill. For example, the standard deviation, S, is required. If we calculate it to be like something like 5, okay, newtons. Or if there's no data, it could be assumed. So if we assume even the margin, like margin K is equals to, K, you calculate it from the manual, you obtain from the manual, M, which is equals to K times S, the K value, now the value of K you insert there, and the value of standard deviation that you obtained here, you put there, and then you get the value here. But if this form also gives you a choice, if you are not given all these values, then you just need to assume. Then if it's specified, you don't need to do all these calculations, okay? You just come outrightly, you say standard deviation, I don't need all that, no need for proportion defective, no need for all that. I just know that the margin that is specified is 5. Yeah. So what will be the target mean strength? The target mean strength will be 20 plus the margin 5 to give you 25. Okay. Then you need the property of cement. Class, we said for the 2.5 and 52.5 is OPC, ordinary Portland cement. The Portland pozzolanic cement is 32.5. Unfortunately, this manual, which is the one that we have currently, we are also using in our country, it doesn't cover Portland pozzolanic cement. So after you design, maybe using this Portland pozzolanic cement, you may need to do some modification. But for our class, we assume that we are going to use ordinary Portland cement, class 42.5. Again, in this form, okay, maybe I may not, I just wanted to highlight how you fill up this form. But this form is a summary of all the steps that you have followed. So if you allow me, we can go back to, I go back to sharing the one that we had before here, because these are the steps. Step 1, select, or stage 1, selection of the target water cement ratio. So first, you need to calculate what is M. Okay, you need to understand what is M. At the same time, then M, you can calculate using K times S. M is the margin, and so on. So therefore, we have done up to part number 3. FM is equals to FC plus M. So we want to obtain the end product of this stage is to get what is the target water cement ratio when we want to achieve our strength. You know, how much water should we use so that we can be able to obtain the strength of concrete that we are anticipating. Okay, so what do we do? This is the step. Now that you have the cement class 42.5, you have the cement class, and now you also need to understand the types of aggregate used. So you go to table 2. So we are going to move to table 2. So I might just have to go back to, you might just need to go back to what? To using this manual. Table 2. Okay. So you come here. We are on step 2. So we come to table 2. Don't worry about this flow chart. This flow chart just tells you how there's different stages. At this time, at this point in time, I would like you to concentrate on this chart. You might get lost, but once you have done the first attempt, then you can come to this chart. You see what we are doing at either of the stage. Okay. Now, our focus on stage 1 is to get the target water cement ratio. So this one we obtained it from this chart. Allow me to minimize this. So what you do, okay, or something interesting. So this table, or this figure 4, you start by assuming a certain water cement ratio of 0.5. So we assume water cement ratio of 0.5. We are assuming, okay, we do not know for the strength of our class, what is the water cement ratio that we could use. But since we do not know, in the manual, we start from a point which is known, water cement ratio of 0.5. This is the starting line as indicated here. Okay. Then what you do, you see we have two curves. We have this straight line and we have these lines that are sloping like this. Okay. So what you do is that you know that your target mean strength, FM, like if in our case we said our characteristic strength is 20, margin of 5, the target mean strength is 25. Okay, so you are coming to where you have, 25 is somewhere. Okay. All right. I don't want to lose anyone so far. So what we are going to obtain is a compressive, a certain concrete mix made with a water cement ratio of 0.5. So the value of the compressive strength will be for that concrete that is made. It is like we do not have the starting value. We do not have the water cement ratio for our target strength. But from practice, from this manual, from empirical data, there is a certain, using a water cement ratio of 0.5, we can obtain a certain strength. Okay. Okay, let's first do it so that you understand what I mean. So what you do is that I think we could have started from table 2. Yeah, table 2. You see, table 2, sorry, I had moved to figure 4 before table 2. Table 2, you see, we are going to obtain an approximate compressive strength of a concrete mix. So we are going to look for another concrete mix, which is made using water cement ratio of 0.5 to form our starting point. So given that we have ordered pottery cement class for 2.5, then what are the aggregates do you have? Usually in our lab, you'll find like we have coarse aggregate will be crushed. But fine aggregate, you know, it's riverside, it's uncrushed. So what is the classification of our aggregate? Coarse aggregates are uncrushed. What is the strength if you are going with 42.5 cement at sorry, not uncrushed, crushed for coarse aggregate. At the crushed coarse aggregate, you are told at 28 days, using this water cement ratio of 0.5, you can produce concrete of of strength 49 MPa. I hope you digest that. So we want to know, to produce a strength of 25 MPa, what will be the water cement ratio? We do not know. So what we are being told is that, coming to table 2, what do you know the properties, the physical properties of the aggregate? Yes. Coarse aggregate? Yes, it's crushed. Do you know the strength of your cement? Yes. OPC for 2.5. Then, if you use those materials and you fix the water cement ratio at 0.5, then at 28 days, you can be able to produce strength of 49. So this is the value you come with it to figure 4. So that's why you find like you are being told, using data from table 2, this is a starting point. You go down this line. Data from 2, okay? Data from figure 2, table 2, you come to figure 4. So you are moving down through this bold line. And then as you move down, because at the end of it all, we want to know the appropriate water cement ratio. So you come down through this line, and I hope you are following your notes. The value of compressive strength is plotted on figure 4. So you see, 49 is around this part. Okay, 49 is around here. So this is 50, 49. You can use your scale rule to see where 49 is, the compressive strength. Okay. Then from this point, a curve is drawn at this point parallel to the printed curve until it intercepts a horizontal line passing through the ordinate representing the target mean strength. Our target strength is 25. So you draw a horizontal line here. Okay, let me just I need to draw a horizontal line. Allow me. So at 25, we draw a horizontal line. That is our target mean strength. Okay. Then that point 49 is the affixation of concrete that we can produce using our aggregate if we maintained our water cement ratio to be 0.5, but we do not want to produce a strength of 49. So we are targeting 25. So now what you do here is that now you draw a line parallel. You draw a line parallel from the point 49, parallel to these curves, parallel to these curves. So it's an approximation kind of, until it intercepts our target mean strength. Then you read downward. You read downward here. You read downward this point. And this will give you what is the water cement ratio that will give you the strength of 25. So we are saying from the characteristic of your aggregate, a water cement ratio of 0.5 would give you a strength of 49. Therefore, through interpolation using these curves, we have found that a water cement ratio of this value, maybe this is 0.777, will give you a strength of 25, which is our target strength. So we have obtained the water cement ratio. And therefore, when you come now to in your table here, you can be able to fill this part. Okay. You can be able to fill in this part. Allow me just to undo this, to delete this. I'm just hoping that I'm not by myself. So in the comments so far, so that I can address it before we go too far. Of course, I know that you need to do a little bit more practice in this before it can sink in your system. But I believe with the guidance, the way we are moving, then it will be very easy for you now to revisit it. So look at it once again, how we have read that value. Okay, as I take a glass of water. All right. Silence means that we are good. Right. Now, I think at this stage, we may need to work with an example so that you're not surprised where I'm getting these values from. So allow me to do what? Allow me to delete all markups. Allow me to delete all markups. I wish there was a faster way of doing this. It seems actually there's a certain line that is not coming off. Okay, don't worry about that. Just giving you time to process all of what we have done so far. Well, there's a line I'm trying to remove here. I don't know why it can't go away. Because I know it's going to affect us. So for that reason, let me just close this first, then I open it again. Okay. And then I want to share an example. We want to work on this. In the meantime, I want to open the manual. Okay. Okay. So you are given an example that reads, using now the method Department of Environment Mix Design Procedure, you are required to design a concrete mix and you are given the following information. So who gives you the following information? Some of the information is what you get from the lab. So you want to design concrete class 25. Now, to avoid a lot of work, instead of getting the standard deviation and all that, since we have not conducted the concrete cube crashing tests and all that, so we have assumed the margin to be 5 Newton per millimeter square. Again, there is something that I want to give you that we are going to study later on. When we are going to learn about the properties of concrete, we studied the properties of concrete in fresh and in hardened state, when it have hardened. So in fresh state, we want a concrete which is workable, which can be able to flow, we can be able to mix, place, compact, vibrate well. So there is a measure of workability that we have. And one of the parameters that we measure is what we call the slump. Slump. Don't worry, at this stage, we are going to explain it as we go by. But the slump basically is the way the word sounds. There is a cone which is inverted. Okay, there is a cone that is inverted. In the lab, you're going to see this. Then the cone itself is filled with concrete. So the slump test, I'm just explaining briefly because we are going to look at it later on. There is a cone, an inverted cone, which is open on both ends, like that, placed on a metallic plate. Then concrete is placed inside here. And then it's rammed using a nylon rod. Okay, you compact it. Then this cone have got handles. You lift it up slowly. So what happens is that you'll be left with a concrete formed in a cone-shaped manner. Once the cone is completely removed, it tends to slump. It tends to slump like that. So we measure this height as the slump from the initial. So how do you measure this? You just take the cone, the steel mold cone, you place it adjacent here. Now you place it in upright position. Then you place a steel rule here so that it can give you a benchmark. Then you measure how much your concrete have slumped. You know, like to slump. That's an English word. I don't know how else I can explain. Collapsed, fallen. Okay. So we say this is a slump value. So depending with if the concrete is, the workability is very high, it is going to slump almost completely. So there is a certain range that we want to obtain our workability. So we specify a certain slump range, that this slump, this height should be between 10 to 30. There are cases whereby we can specify between 0 and 10, 10 to 30, and so on and so forth. Then we may also specify other issues. We do not want too much water, so we may limit the amount of water that we may require. At this stage, remove this requirement. Then we are told that we are using ordinary Portland cement. From your laboratory work, you have determined the properties of this aggregate. Fine aggregate, you have seen this riverside, so it's uncrushed, and you have determined the absorption capacity to be 0.23. Now you also determined from the grading, you need to determine the percentage of fine aggregate passing 0.6 millimeter sieve. So from your grading, you need to be careful. Like we started with 4.75, we came to 2.36, 1.18. Where we had 600, you need to determine the amount passing that compared to the total so that you can get a percentage. Again, for coarse aggregates, you dealt with them. The ballast was crushed. Absorption capacity, you determined 0.91. So then the specific gravity of the aggregates determined it to be 2.5. And you are told that the maximum size of aggregate to be used in your concrete should not exceed 20. So when you're told to design, we want to see what is the ratio. What will be the ratio of cement is to fine aggregate, is to coarse aggregate, okay? And also what is the water cement ratio to achieve that characteristic strength. So let us work with this example so that we can move with all information. Now you have all information. Some of it we are going to understand more as we study the properties of concrete. Now, so it's very simple. First, stage one, you're going to do what? The stage one, we are going to determine what is the target mean strength. FM is equals to FC plus the margin. So this is 25 plus 5. This is 30 MPa. So fill that in your graph. Number 2, with this, remember stage 1, we are determining what is the target water cement ratio. So we need to go to table 2. Okay, table 2 in the manual, and from table 2, you need to determine based on the aggregate that you are given. The coarse aggregate is crushed. We are using OPC. When you are given OPC, is it mentioned somewhere? The cement, yeah, cement OPC. OPC, we could have been told is 42.5. Okay, MPa. So from table 2, you can be able to obtain, as we did before, that using a water cement ratio of 0.5 and the characteristic of the coarse aggregate we have and the cement, you can be able to produce cement of 49, concrete of 49 MPa. All right. So far, so good. I will start moving a little bit with speed. I'm seeing time is not on our side. Okay. So I have summarized the workings, but I've used a different sheet, different from what the BRE has. So I've summarized my calculations because the sheet that is in the BRE manual doesn't show that they have written for you, but when you're doing your working, I want to see this. So the characteristic strength is 25. Then the margin, either you calculate using equation C1 in the manual, or you can specify, assume it was specified. So it's specified at 5. The target mean strength, 25 plus 5 is 30. Then from table 2, so you need to mention these references. From the manual, you need to mention which equations, which tables, which figures are you referring to. Why I'm not going back to table 2 is because you have already read with you that using a crushed coarse aggregate and cement OPC of 42.5 and a fixed water cement ratio of 0.5, then okay, we are able to obtain a certain concrete of this strength. Then to obtain the free water cement ratio, we have read with you in figure 4. We have read with you in figure 4 that the water cement ratio. Maybe now for our case here, we can read it again. No, we already read. It's going to behave the same because you just need to draw a line. Before you are drawing a line at 20, now you draw your line at 25. Then from 49, you draw, a line. Then where it intercepts 25, you read the water cement ratio. But from this given information, okay, from the given information here in this, you are told that the maximum water cement ratio should be 0.6. So from your table, you look at it again. The table says, from the table you obtain that the free water cement ratio is 0.68. I mean, figure 4. But this maximum specified is 0.6. So it means we go with the maximum value, the lower of the 2, because you are told you can't exceed this, 0.6. I think we have done calculation up to that point with you. And if you go back now, if I go back to now the manual, if I go back to manual, yeah. So I'm back the manual. And if you look at this, even before I go to the manual, let me show you from your notes. We are done with step 1. Okay. Remember, stage 1 involved what? Selecting the target water cement ratio. So we have gotten the output of stage 1, that the target water cement ratio has to come to 0.6. So you have the output of that. So we go to step 2. We want to select the free water content. What is this? Water cement ratio is water over cement. It's a ratio. And we said when we are specifying or when we are designing our concrete, or even when we are mixing, we always provide water as a ratio, a proportion of the cement. So if we know this ratio is 0.6 already we have calculated, then we want to know how much water now, free water, that is required. So what does that tell you? We need to determine first the quantity of cement that is required. So to do so, we go to table 3. So let me go back now, share. I'm sharing between screens, so I know today you may feel like we are jogging in too much. But one thing I know is that you have your manual, so it's very easy to move, not like me. So we move to table 3. So table 3, if you read table 3, remember the steps that I'm giving you are these steps listed here. Like we are on step number 2, selection of free water cement ratio. We are on subsection 5.2 of the manual. So you come to table 3. What does the table 3 say? If you look at table 3, it says, it gives you us, the title of the table is approximate free water content. Of course, we are designing per cubic meter of concrete or per unit. The approximate free water content required to give various levels of workability. So it means you must have the workability. You must have that level of how workable do you want your concrete to be, so that now you know how much water you need to include or to provide for in your concrete, right? Now, what you realize is that we have already been specified the slump, and our slump was given to be between what? I hope the question is clear to me. The slump was given to be 10 to 30, specified slump between 10 and 30. So what we are saying is that here, if I can use the pencil tool, we are reading this line, 10 to 30. Forget about the second row, the VB time. This is another parameter that can be used, another measure of workability. You are going to see it in the lab. But for our case, you don't have to use both of them. If you are given the slump, you stick with the slump. The VB time, you stick with that. But we are going to see in the lab, what does this mean? Okay, so if we are now the target, the specified water slump is between 10 to 30, okay? And now, in our example, we are told, I hope that question you noted it. I don't know whether you people, you are writing it. The maximum size of aggregate was 20. Okay. Now, the type of aggregate. In table 2, we were told it's coarse aggregate. But now here, we are not told the type of aggregate. Therefore, do we say it's uncrushed or crushed? If it's uncrushed, both of them, we would have gone with the first, with this row. However, we are using 2 different types of aggregates. The coarse aggregate is crushed. The fine aggregate is uncrushed. So which value do we read between these 2? Okay. Because that's where it falls. We are on maximum size of 20. We are slump of between 10 to 30. However, our aggregates are average. I mean, our aggregates have got 2 types. To understand now what you need to do here, if it can't be read directly, there is a footnote. There is a footnote here. Okay. There is a footnote below the table. What does the footnote say? The footnote says, when coarse and fine aggregates of different types are used, the free water content is estimated by this expression. Okay. Okay. 2/3 of WF, where F is the free water content of the fine aggregate, and 1/3 of WC. Okay. Therefore, what do we need to do here? Since they are of different types, we read them separately. Okay. We read them separately. We are saying for the coarse aggregate, they are crushed, so we take 190. For the fine aggregates, they are uncrushed, so we take 160. Therefore, our formula will be 2/3 times 160 plus 1/3 times 190. Okay, so this only happens when we are using aggregates of different type. So I go back here to our working. So we are saying from table 3, the free water content that we are determining will be given by, because we have aggregates of different types, 2/3 the value for the fine aggregate uncrushed, 1/3 the value of coarse aggregate crushed. Okay. Remember, of course, you are reading the column of 10 to 30, and the maximum size of aggregate as 20. So when you do this calculation, you are going to see that the amount of water is 170 kilograms per meter cubed. And therefore, if we had water to cement ratio is 0.6, and we have determined the amount of water to be 170, what does this tell you? That we can be able to get amount of cement as 170 over 0.6, which is this. To get it as 2.283, and then I've just rounded it off. Maybe you don't have to round it off at this stage, but when we are concluding the ratios, the manual says we give it to the nearest value of 5. That manual, that page 11, where we are filling in, if you move what? If you go to the bottom where you are doing your summary, it says when you are writing the quantity of cement, water, fine aggregate, coarse aggregate, the second blank row line, it says per meter cubed to the nearest 5 kilograms. Okay, that's why now I'm already doing it here at this stage, but you don't have to do it here because it will affect other ratio here. So this tells you what? If we go back now to, our notes, or even the manual itself, if you go back to our note, we have covered step 2. Okay, we have covered stage 3. We have found what is the amount of free water using this formula because of using different types of aggregate, and maximum size of aggregate was given. Okay, so you have found that the amount of water is 170 kilograms per meter cubed. Then going ahead, we have also done stage 3. So I think the part which was a little bit difficult was just stage 1. So stage 3, determining the cement content. Already we have done the cement content. We said the water to cement ratio is given. Free water to cement ratio is given as 0.6 from stage 1. From stage 2, we have gotten the amount of water, which is 170. So we can be able to calculate the amount of cement as 285 or 283 point whatever kilograms per meter cubed. So if this is a note I'm giving here, if now again the requirement, you had the requirement for maximum or minimum value of cement, you always check against the requirement, the design requirement. Maybe you could have been told that the cement requirement should not exceed 280. Okay, so you go with the minimum. And maybe you could have been told the minimum cement requirement should not be less than 290. Therefore, you go with the minimum. Okay, there is always good to be checking out that. And here I'm giving, this is not part of the manual, but it's from some others, Murdoch et al. In 1991. They found that this is from experiments. So this one, don't put it in manual, but just note that if, for example, for the grade of concrete, if our grade of concrete is 25, okay, with a free water cement ratio, generally for you to obtain this class, you may be going with maximum, the water cement ratio not to exceed this, and the minimum cement content to be within this range. Okay. Okay. But anyway, for our case here, we are not concerned with the Murdoch. It's just like this is his calculation. So don't worry about that. We have obtained the cement content. Okay. The cement content. So the minimum is ours was 285. So it was above the minimum. It's okay. Our water cement ratio is 0.6 below 0.7. So we are good. So we have done stage 3. So we move to stage 4. We already have determined the amount of water, the amount of cement per cubic meter of concrete. Now, what else do we need? We need to determine the amount of aggregates. So, and this is what we do. We determine the total aggregate combined, and then we separate to see the quantity for fine aggregate and coarse aggregate. Okay. To do so, we need to utilize the density that you determine the lab, the density of the aggregate. So we go to figure 5. So the density, of course, of your concrete will determine the density of the aggregate. Of course, even the density of the other ingredient. So how do you obtain this? We go to figure 5. This aggregate is determined in saturated surface dry condition. Of course, I know you are doing your lab works, and you should be doing this by now if you are moving in a proper pace. So we go to table or to figure 5. So back again to and fro. I go to the manual. I go to, we are going to table figure 5. So what about figure 5? In figure 5, we are going to determine the density, the wet density of concrete. So you see here at the bottom, we have the free water cement ratio. Okay. Sorry. Let me use an annotation. So we have the free water cement ratio. Free water content, which became 170, around that amount. Okay. Then the questions, from the question we had done from the lab, we had already determined the aggregate, specific gravity of the aggregate as 2.5. So we have this line 2.5. Okay, you see this line 2.5. So these lines are read from this end. Okay, then we have here. So what do? You draw a line like that to intersect 2.5. Then you read the density of the wet concrete. Now, if let's say the density was given as 2.55, so that 2.55 is here. Let's say that the density of the aggregate was 2.55. You would have drawn a line parallel to this. How do you draw a line parallel? Noting that the gap here might not be the same as the gap here. And this one is clearly outlined in figure 4. The first figure that we started with, figure 4, the curves, the starting point was narrow, then as you go down, it was widened. So what you do is that you mark here, you use a scale, your rule, scale rule here, so that you know where, if you are here, 2.55 is. Then you come to this point, You measure where 2.55 is. Then you draw your line. So this is the case if the value of the specific gravity of your aggregate does not fall within the already plotted line. You may need to generate your line. But for our case here, the line was given. So you just need to read 170, where it meets 2.5, then you read across. It's around 23 watt. So you can read it carefully with the ruler. For me, I read it to be around 2315 kilograms per meter cubed. So we have obtained the density of the total mix. So going back to our is it notes? Let's go back to the notes. So the total aggregate, total density of wet concrete, we have found it to be 2315. To get the density of the aggregate, which of course is the weight per cubic meter. You see the density is, it will be kilogram per meter cubed. So if we are talking of a cubic meter of concrete, so we are going to get the weight of the aggregate. So this tells you that we need to subtract the total density, we subtract the weight of cement minus the weight of water. Cement was 285, water was 17, and this is 2315. What value do you get? Okay. The value is about 1860 kilograms per meter cubed. Okay. And that's it, stage 4. You see, it's very easy once we have done stage 1 and 2. So the last stage now, because now we have the total aggregate, how do we know out of the total aggregate of 1860 kilograms per meter cubed of concrete, how much of it is fine aggregate, how much of it is coarse aggregate? Now, to do so, we are going to read the theory behind this later on. We want to determine the amount of materials finer. From your grading, you do your grading. Okay? You do your grading curve like this. So this is percentage finer or percentage passing, and then this is the sieve size. So we get the sieve size at 600 micrometers. We want to get the amount that is below, that is passing this. Or it's assumed that below 600 or 0.6 millimeter sieve, how fine, this is like an indicator of how fine your aggregate or your SARDIS. Again, you also need to have what you call the fineness modulus. Okay, let me go step by step. So this value now, to determine the proportion of fine aggregate, we read it from figure 6. Okay, and the amount that we read will determine the maximum size of aggregate, and our maximum size is 20 millimeters. The workability level, ours was specified between 10 to 30. And the grading of fine aggregate, which we are saying, can you get the proportion of fines passing 0.6 millimeter sieve or 600 micrometer sieve? And the free water content. So the proportion is dependent on all these. And after you obtain that, then you are going to multiply to say the fine aggregate is the total aggregate times the proportion of fines that are required. The coarse aggregate is the total aggregate minus fine aggregate. Okay. Okay. So as simple as that. So let's see how we obtain this from figure 6. So I take you back to the manual. Open your manual on figure 6. So figure 6 have got a certain number of parts. We said one of the this proportion that we are determining will be dependent on one, the maximum size of aggregate. So you see, we have different parts. Like here, the maximum size of the aggregate, we have 10. Okay. Is our maximum size of aggregate 10? No. So we move away from that. We go to the next set of tables. Is our maximum size of aggregate 20? Yes. So we are using this. If it was not 20, if it was 40, we could have used this. So first of all, you need to settle on the maximum size of aggregate to help you determine which charts are you reading. So figure 6 have got 3 parts. And that's what you are seeing here. It's indicated as continued. Okay. Here it's indicated as continued. I hope this one is not disturbing. So you see, continue. Okay. Then, all right. Let me just move this one slightly down. I'm truly trusting that all these efforts, you guys, you are following later on. So I was saying, you can see this figure 2 is said continued because it's continued in the next figure. Now, here, now that we have noted or we have settled on the charts that we are going to read, since our maximum size of aggregate was specified as 20, then out of the 4 charts, you select the one that falls within the workability. Our workability is 10 to 30. So we are reading this chart. Then when you go inside this chart, you see the bottom, the horizontal axis is the free water cement ratio. What was ours? Ours is 0.6, the one you calculated in stage 1. Then the proportion of fines. This is the proportion that we want to get so that we know how much of the fine aggregate need to be calculated. So what you do here is that these are the proportion of fine passing 600 micrometer sieve. And from our definition of our problem, of course, this is the data that you obtain from the lab. From definition of our problem, we have been told that the percentage of fine aggregate passing 0.6 millimeter sieve is 55%. So you see, this is what I was saying. Now it's falling in between 40 and 60, 55. How do we get this 55? Because we need to plot this line. You just need to calibrate here to mark where 55 is. This side where 55 is, you draw a straight line there. The other one that we were looking at, figure 2, is the one that is a little bit, figure 4 is the one that's a little bit confusing because that one, it were curves. Okay. So now that we have this line of 55, what you do is that you come to 0.6, you move to where it meets 55, then you read across. This across, the value here, which is this value here, will tell you the proportion of fine aggregate that is required. Okay. So if you read this value, to me, it came to around that 3%. You can read it clearly, that 3%. So that now if I go, but because I don't want to come here again, I do not want to come here again in this chart. So I can just write it here. So we are saying fine aggregate equals total aggregate times the percentage of fines. So this will be 1860 times that 3%. And when you do this calculation, you obtain something to do with what? 615 kilograms per meter cubed. So what is the proportion of coarse aggregate? Coarse aggregate will be the total aggregate minus the fine aggregate, which is equals to 1860 minus 615 to give you 1245 kilograms per meter cubed. Okay. And now you have gotten all the ratios. Like you have cement. Cement is water. Your water was 1760. Cement is, I think, 285. Fine aggregate is 615. Coarse aggregate is 1245. And you can express your water in terms of water to cement ratio, which is 0.6. Now, sometimes coarse aggregate may just contain maybe like 2 specific. This is very common when we are producing concrete of a specific, maybe especially maybe high strength. We may say we want to have 2 specific sizes of coarse aggregate, maybe size 10 and size 20. or size 10, 20, and maybe 40. And the manual here tells you, this is why I said I didn't want to get out of this page. The manual here specifies that if you are going to combine, I wish we could get this. The rubber clear. Okay. Now it tells you that the coarse aggregate itself can be subdivided into single size. For example, 10 millimeter, 20 millimeter, 40 millimeter, etc. So if you are combining 10 and 20, the ratio will be 1 to 2. If you are combining 20 and 40, the ratio could be 1.5, 3. So if you are specified or you want to use two sizes, 10 millimeters and 20 millimeters, then the ratio will be 1 to 2. So what does this say? Our cement, water was what? Cement was 285. Fine aggregate was 615. Coarse aggregate now, we have the 10 millimeter and the 20 millimeter. So you subdivide the 1245 in the ratio 1:2 to get the 10 millimeter as around 415 kilograms and the 20 millimeter around 825. But anyway, don't be worried too much about this part. I'm just giving more information on the same. Of course, there are other modifications that can be done, especially when we have the water absorption changing, affecting that. But so far, if you can be able to come up to this stage where you're having all these, you have done mixed proportion. So what happens is that now, because these are ratios per a meter cubed, but a meter cubed of concrete is too much. Okay, so you may just require a small sample, maybe like how many meter cubed, maybe just 0.1 meter cubed. Okay, so you just need to divide by 0.1, 0.1. You say you want to weigh 28.5 kg, depending with the quantity of concrete that you require. Okay, doing so, you get the ratio. So the best thing to do is, instead of expressing it or leaving it like this, express it as a ratio of cement. So divide through by 285, by 285, by 285, so that you shall see this one will be 1. This one will give you a certain value. I don't know, 615 by 285 is what? I believe should be 1 point something, and then the other one gives you maybe 2 point or 3 point something. And then you know that that is the ratio that you have designed. So what remains is just to create trial mixes using this ratio. You cure them, you test them to see whether you have attained your designed strength. Okay. So I would like to continue from that point. So if I can show you where I have summarized all that. Okay. This is my summary page. This is my summary page. Why is it appearing here? Oh, it was writing on the screen. So I can stop sharing. So then I share my summary. So this is the summary of the calculation that we are doing. I have summarized it in one page, okay, in a single page. If I minimize it, I don't know whether you'll be able to see it. So I have summarized the calculations, giving references, giving the output, the final aggregate and all that. And so far, we have done up to this part. And in the interest of time and for the sake of understanding, I would like to reach there. We may need to adjust our ratios because we have the absorption ratio or capacity of our aggregate. And that is explained in the manual when you want to find the actual amount of water that is required, considering that these aggregates are thirsty and are going to take water. So you might need to add extra water, additional water. But for today, let's now digest that, how you come up all the way up to that point with the ratios. Then later on, you can look at how you adjust for absorption water. I'm looking at the comment section. I still feel nobody have raised any concern, any question. To me, I believe that that shows that you're understanding quite well. Yeah. Or maybe the question you would like to ask cannot be, it's difficult to write down. But instead of asking a question at this stage, giving you a link to come to Zoom, of course, all of you can't see it. I'd like you to go through what we have just discussed today. And if you have any concern or question, discuss it amongst yourself. If you have any concern or question, then you can always raise it in our subsequent classes. Okay. So thank you for appearing. I know you are tired from the workshop, but at least we were able to handle that. I didn't want to lose this class because the time is far much spent. So let's continue doing our studies. Allow me to stop it at that.